Okay, brief revision about trigonometry. The first you learned was in a right-angled triangle with respect to some angle phi. There is an adjacent leg, an opposite leg, and a hypotenuse. We then defined functions like the sine of phi to be the ratio opposite leg over hypotenuse. Likewise, for the cosine of phi, this was adjacent over hypotenuse, and for the tangent of phi, we had the opposite leg over the adjacent leg. Using these three relations, you could compute arbitrary right-angled triangles. You're asked to do this again in the exercises. We then moved on and considered more general cases. We introduced two general formulae that hold in arbitrary triangles. This was the sine rule, a over sine of alpha, not plus but equals b over the sine of beta equals c over the sine of gamma. Using this sine rule, you could compute arbitrary triangles whenever you had the following situation. Say you pick these two here. If you know A, if you know alpha, and if you know beta, you can obviously solve the equation for B. Okay, that's how the sine rule is used. Similarly, for the cosine rule, we had c squared equals a squared plus b squared minus 2ab times the cosine of gamma. And again, the formula holds in arbitrary triangles. If it were right angles, then it would be reduced to this, as gamma then would actually be 90 degrees. Cosine of 90 degrees is 0, and the cosine rule is reduced to the theorem of Pythagoras. I think that's worth memorizing. It perhaps facilitates memorizing the cosine rule. Okay? Now, cosine rule, you use the cosine rule whenever you want to compute a side given the other two sides and the angle enclosed by the two sides, as is that's sort of the prototypical use. You can of course also use the cosine rule to solve it for the angle. If you know all three sides, you can compute the angle. Okay, that's how you use trigonometry in or with triangles. Now, actually, to state the sine rule and the cosine rule, we had to extend the definition of sine and cosine, because from the first definition it's not immediately clear what, or it's not at all clear actually, what the sine of, say, 100 degrees should be. We then introduced the unit circle to extend the definition of sine and cosine. The unit circle is a circle centered. The idea is it is centered at the origin of a coordinate system and has radius 1. Okay, something like this. That's 1, that's 1 also. We then draw our angle in question here, and the point we get on the circumference of the unit circle is P, with x being the cosine of phi and y being the sine of phi. Again, phi is the angle here, measured from the positive x-axis, and cosine is just the x-coordinate of the point, and y is the sine. The y-coordinate is the sine. Okay, that's a definition, a new definition, which allows us to extend sine and cosine for arbitrary angles. Okay, naturally for obtuse angles, as we used in sine and cosine rule, but actually for any angles at all. If we look at this, we realize that we haven't defined the tangent yet. The tangent of phi would actually be opposite leg over adjacent leg. We can still use that here. This is S, this is C, sine, cosine. So actually the tangent of phi would be the opposite leg sine of phi divided by the adjacent leg cosine of phi, which is a definition we can use for the tangent. Okay, it has always been true, but now it's actually worth memorizing this formula. Yes, something else. If we look at the right-angled triangle, we notice its hypotenuse is 1, and this immediately tells us that the cosine squared, cosine of phi all squared, which is usually written like this, cosine squared of phi, plus the sine of phi all squared, the second leg, all squared, well, that's, according to Pythagoras, the hypotenuse squared. So this is 1. No matter what phi is, if you add the squared, cosine and sine, you'll always get 1. That's clearly worth memorizing too. It's Pythagoras with trigonometry. Okay? Now, one question that has always been quite unclear is how does the calculator compute such sine or cosine values? When I introduced the trigonometric functions, I showed you that book with extensive tables containing sine and cosine and more stuff, okay? And students used to look that up, actually. Only when the calculator became available, advanced calculators became available in the late 70s, I'd say, have students been able to actually type that in. So what does the calculator do when you type in the sine of, say, 51.4 degrees? Sorry, sine of, say, 21.7 degrees. What does your calculator do? First of all, it converts this into radians. We seized the opportunity, of course, to revise radians. Yes, pi over 180 is the factor times 21.7 degrees. What we get is, in radians, this is approximately 0.379 radians, okay? So we want the sine of 0.379 radians. Now, if we look at the graph, oops, that's the wrong picture, sorry, the wrong picture. Where is the good picture? Here it is, the good picture, yes. If we look at this graph, sine graph red, so 0.37, that's perhaps here, approximately. If we try to compute the sine, well, then it's here. I don't know, 0.4 or something, 0.4-ish. The trick is the following. We state the equation of the tangent. That's the tangent. It's clearly of the form a plus bx, okay? Because it's a straight line, it has the form of a linear equation, a plus bx for some numbers a and b. Now, as you see, it doesn't matter that much whether you use the actual sine graph or its tangent at x equals 0 to compute that value sine of 0.378. Okay? Of course you'll make a mistake. If the farther away you are from 0, the larger the mistake is. If you compute the sine of 1 that way, then you do make a mistake. However, the trick now is, why stop at the tangent? Why not try to match a more complicated polynomial as this third degree cubic polynomial at sine? This is something of the form c of x, or let's just call it p of x as in polynomial, which is a plus bx plus cx squared plus dx cubed. You practiced stating such functions, right? Why not try to state such a function that matches as closely as possible the graph of the sine function? We look at x equals 0. We surely want p of 0 to be sine of 0. For the tangent, if we had also used this, I'll be a bit sloppy here, okay? Sine dash of, we all know it's cosine of 0 actually. And that's the gradient, right? Now, why not go on like this and ask similar questions, have similar constraints on the second and even third derivatives? I think you agree that this system of equations with 4 equations is sufficient to determine all these coefficients a, b, c, and d for our polynomial, using not only the y value and the gradient, but also the second and the third derivative. Okay? This is what is called Taylor series or Taylor expansion. And the next video, not by myself, but by 3 Blue, 1 Brown, it is presented quite neatly.